Welcome back, everyone. So in the first segment, we developed hopefully an appreciation or historical understanding of where the concept of limit came from. So these are not just random topics. Usually there's a reason why mathematicians are interested in studying a concept. And so now that we've understood, hopefully, a little bit motivation behind why we're setting limits, now we're going to take a look at some definitions and examples to understand how do we find the limit of a function as x approaches to a finite value. And at a future lesson, we're also going to take a look at limits as x approaches infinity. So these were the goals that we had set out on the first lesson. So I showed you them already, but take a look again. So we're going to look at the definition, understand the difference between function value versus limit as x approaches c, and also determine the limit using three ways: graphing, table or numerical approach, and finally an analytical or algebraic approach. So let's get started. So first, let's look at the definition of a limit. And before we even look at the definition, let's remember something about something we've learned in algebra, the function value. So we need to understand the function value really well before we can add on a new topic. So here we have a function y equals f of x, and it has a point of discontinuity, right? At the points x equals to c, this function it has a hole here and has a filled in dot there. So this is really where it's defined. And here it has a discontinuity. So if I say, what is the function value at the point C? Look, y equals f of x. So what is f of c? So take a look at the y value. So which one of those would be your y value? So you would probably agree with me if I write m, right? So the function is at the point C. You go to the filled in dot. And at that point, you look at the y coordinate. So at that point, the function is defined as m. Okay, now let's talk a little bit about the limit as x approaches to c. So when we do that, we will approach from the left-hand side and from the right-hand side. And regardless of what happens at the point c, we want to see what is happening to the y coordinates. So as you are trying to approach towards the point C along the curve, okay, think about what is happening to the y coordinates. So the y coordinates are approaching this y value, right, which happens to be L. So there we would say that the limit as x approaches C of the function f of x is equal to L. So one thing I want you to notice here is that the function value did not necessarily match the limit value, right? So in other words, a function can be discontinuous at a given point, but the limit can still exist because the limit doesn't really care that much about what happens at the value, but the real purpose of the limit is to figure out what happens as we approach the value infinitely close from both directions, from the left and the right. We'll talk more about that in a minute. So basically a very simple definition we can give at the moment. We can say that if the function values of a y equals f of x approach L as the x values approach c from both sides, then we say that f of x has limit L as x goes to c. And this is how we write it. And I've already written it down the same way. Now let's clarify this a little bit further, because I talked about approaching from the left and approaching from the right. So we're going to use this notation, limit as x goes to c from the left. So if I put a little negation sign above c, that means we're approaching from the left. So that represents the limit of f of x as x approaches c from the left. And limit as x goes to c, if I put a little plus sign above the number c, c again will be representing a value along the x-axis. That means we're approaching the function f of x as x goes to c from the right-hand side. Now the first example we're going to do is just going to be looking at a picture. Suppose we don't even know the equation, and we're going to try to figure the limit using a picture or a graph. And it's important to notice that in order for a limit as x goes to c for a function f of x to exist, we need the limit from the left to equal to the limit from the right. If one approaches one value, another approaches another value, and they don't match, then the limit does not exist at that value. Okay, so let's take a look at this example. So we have a piecewise defined function here where, for example, we can see right away that the function is not defined. Rather, it's not continuous at -4, right? Because there's a break in the graph, right? The function is not continuous at 2. Also, right here, there's a hole. The function is not continuous at 4. So one thing we learned in algebra is like if you basically can draw a function without lifting your pencil off the paper, basically you have a continuous function. Anytime there's a break, a gap, and vertical asymptote, then you have a function that is not continuous on certain values. So based on this graph that we have for y equals f of x, let's figure out the following questions. The first few are going to be things that we already know from algebra, like function value at 1, function value at 2, etc. For example, the function value at 1 would be, just go to the function, draw a vertical line, and wherever it crosses the graph, read the y value there, so f of 1 is equal to 3. What about f of 2? F of 2, go to the function. Okay, do you go this way? Do you go that way? Well, there's a hole here, so come down to the filled in point, and there the y-coordinate is -1. So hopefully this is nothing new. We've talked about functions in algebra before, right? F of 4, so go to the, okay, here's an interesting case. Go to the function, there's an open hole, right? So at that point, and there's nothing like a filled in dot like over here or anything like that, so F of 4 is undefined. The function basically is not continuous there. So not defined at 4. Okay, what about -2? At -2, go to the function. You see the y value right there. It's 1. At -4, looks like the y value, okay, you can come down or you can go up. We're going to go up because the filled in point is on the top there. So at -4, the function is defined as 3. Okay, so now that we've reviewed function values, let's tackle the limit questions, such as, let's determine the limit as x goes to 2, and the little negative on the top of 2, remember, doesn't mean the number is negative, it means we're approaching to 2 from the left-hand side. So here is the point 2. Let me clear that graph a little bit, deleting those extra green dots. Okay, so approaching to 2 from the left-hand side. So we're going to follow the curve. And as I'm approaching to 2 from the left-hand side, look at what's happening to the y-coordinates. The y-coordinates are approaching the y-coordinate of this point, right? Which is -1. So limit as x goes to 2 from the left of this function is -1. Now, what do you think is the limit as x goes to 2 from the right-hand side? So the curve, as you approach to 2 from the right-hand side, will take us in this direction, then this way, approaching to 2 from the right-hand side, and basically think about you're following this path, approaching towards x equals to 2 along that path. Look at what's happening to the y values this time. Y values are going to approach the y value of this point. So even though it's not defined there, the y values are approaching that value, which happens to be 5. Now, did the limit from the left and the right match? The answer is no. One was -1, the other one was 5. Therefore, in general, limit as x approaches to 2, we say it does not exist because the limit from the left is not equal to the limit from the right-hand side. Okay, so I'm going to give you a few moments now to answer the same question for limit as x goes to 4 from the left and from the right and from both sides. So take a few moments, pause the video if you like, and then come back and check your answers. So as x approaches to 4 from the left-hand side, so we follow the path of the curve and pay attention to what's happening to the y coordinates as we are approaching to x is equal to 4 along the curve. And the y coordinates are going to approach the y coordinate of this point, which happens to be 2. So approaching from the left, we get a limit of 2. Approaching from the right-hand side of 4, again following along the curve, approaching from the right-hand side of 4. So the y values are once again approaching the y value of this point right here, which is 2. And because those two values are the same, the limit equals to 2. In general, limit as x goes to 4 of f of x is equal to 2. So once again now, try the same question for x approaching to negative 1. So approaching to negative 1 from the left-hand side, the y values are approaching towards 4. Approaching to negative 1 from the right-hand side, we will get the same. And in general, then the limit exists and it's equal to 4 as x is approaching to negative 1 from either direction. And let's also answer the question approaching negative 4 from the left, right, and both directions. Approaching to negative 4 from the left, y is approaching to 3. Approaching to negative 4 from the right, y is going to negative 2. So 3 and negative 2. And because these are not the same, this limit does not exist. Finally, approaching to negative 2. Approaching to negative 2 from the left, the y values are approaching 1. Approaching negative 2 from the right, again we're getting 1, right? Therefore, this limit will exist and will equal to 1. So let me summarize something about what we've learned here. So for example, around the point negative 4, approaching from the left, we got 3 for the limit. Approaching from the right, we got negative 2, and they were not the same. And the function value was 3. So the limit didn't exist, but the function value did, right? But approaching to this point, x equals to negative 1 from the right and from the left, we got to the same value. So the limit existed there, which was also the same value for the function value. So f of negative 1, if you remember, or maybe we didn't answer that. Let's see. F of negative 1 is the same as 4, but the limit as x approaches to negative 1 is also 4. So there are some situations where the limit can be equal to the function value, but there are other situations the limit will differ from the function value. Like here, the limit didn't even exist. The function value, on the other hand, was 3. Here, for example, the limit was approaching from the right and approaching from the left. As x goes towards 4, the limit did exist. It was 2. The function value didn't exist, right? Because there was a hole there. So again, they are independent of each other. What happens at the point does not necessarily have to match what happens around the point. Sometimes they do if the function is continuous, like in this case, but they don't have to match. Okay, let's do another example. All right, let's take a look at this one. The question is, what is the limit for this function as x approaches to negative 2? So if they don't give us a little plus sign or a little minus sign, we must consider from both directions. So it's always a good idea to pause the video for a few seconds, answer it on your own, and then come back and check your answer. And do this often, I think you're going to get the most out of the videos if you do that. So as x goes to negative 2 from the left-hand side, the y values are approaching towards negative 5. As x approaches to negative 2 from the right-hand side, the y values are also approaching to negative 5, right? Therefore, this limit is going to be equal to negative 5. All right, next we're going to do something a little bit different. We're going to look at an equation because they don't always have to give us a graph. They can give us an equation and still ask us to find the limit. And we're going to try to develop an approach where we don't have to have a graph to have an answer. So for example, let's find the limit of x squared as x goes to 3. Now, At the moment, I will show you the graph, but slowly we're going to move away from depending on the graphs. So f of x equals x squared, we know is a parabola, and at x is equal to 3, we know the y value because 3 squared is 9. We expect that the y value there is going to be 9. So as you approach from the left-hand side and the right-hand side, what do you think will be the limit as you approach from the left-hand side and as you approach from the right-hand side? Where the y value is going to approach, and if you said 9, that is indeed the correct answer. And for this question also, try plugging 3 directly into the function. You would have gotten 9, right? So this is what I'm going to call one of the easier cases where you plug the value in and you get the same answer as the limit question. So the limit as x goes to 3 and the function value at 3, they match. And you're going to see that this is the case anytime you have a continuous function. If there's no jumps, no gaps, you're trying to find the limit as x approaches to 3 on that graph, approaching to 3 from the left and from the right will lead to the same value at the same point 3. All right, what about x cubed minus 1? Well, again, if you first look at the graph, y equals x cubed, we know looks something like this. X cubed minus 1 is the graph pulled 1 unit downwards. So this being negative 1. Now we're taking a limit as x goes to 0. So approaching to x equals 0 along this graph, approach from the left-hand side, approach from the right-hand side, and where are the y values approaching? They're approaching to this y value of negative 1. Now, if you did not know that and simply plug the 0 into the function, what would you have obtained? 0 to the third is 0, minus 1, you would still get negative 1. So again, these are the easy cases where the function is continuous, and to be able to determine the limit, all you have to do is really, you don't even have to look at a graph. Just plug the number in and you're going to get an answer. That will be your limit, the answer to your limit question. So what I just said there is written more officially as follows. For a continuous function with no holes, gaps, or asymptotes, the limit as x goes to c will be the same as the function value at that point. In other words, the limit equals the function value. All you have to do is plug the c in for x and you're going to have the answer. How do you know when it's continuous and when it's not? Well, I would say start by substituting the value in. If you get a good, decent, well-defined value, you are fine. You can just do it that way. If on the other hand you get like a division by 0 or simple 0 over 0, some weird situation like that, then the function is not continuous there. We're going to have to learn other methods. That's going to be in the next segment. But right now, let's resolve the easier cases where the function is continuous. So in each of these examples, determine the limit. So basically, anytime you see a limit question, the first thing you should try to do is plug the value in. If that gives you an answer, you need to do nothing else. You have gotten the answer to the limit question. So for example, let's substitute 2 in for x. 2 squared is 4, minus 10, 5 times 2, plus 6. So here I'm getting 4 minus 10 is negative 6, plus 6, I'm getting 0. So the limit is going to be 0. And if you graph this function and look at what's happening around x equals to 2, you see the y values are approaching to 0. Take a look at this next example on the right side, please. Once again, if you know nothing about the problem, always a good idea to start plugging the value in. X is equal to 2. So here we have the square root of 3 times 2 squared, or 4, minus 9. So 12 minus 9, or 3. So our answer is going to be square root of 3. So that's the limit which matches the function value. So remember, these are your easier ones. And for the more challenging or interesting cases, check out the next segment. So if x is going to 3, or rather x is going to pi over 3, just simply plug in pi over 3 in for x. And here, hopefully you're remembering some of your trig function values. So this is sine of pi over 3 over cosine of pi over 3. Pi over 3 is 60 degrees. And sine of 60 is radical 3 over 2. Cosine 60 is 1 over 2. And their ratio will be radical 3. Similarly, limit of sine x as x goes to pi over 2 by simply substituting this in. Sine function is a continuous function at pi over 2 or 90 degrees. Hopefully you remember your unit circle, right? Right up here you have the coordinates of 0, 1. First one representing cosine pi over 2, second one representing sine of pi over 2. The answer is 1. And finally, limit of cosine x as x goes to pi over 4. That will be cosine of pi over 4 or cosine of 45 degrees. And that is the same as sine of pi over 4, right, in case you ever need it. And they're both equal to radical 2 over 2. So all of these are the easier cases where we plug the value in, got an answer that pretty much tells us that the function was continuous there, and the limit therefore will equal to the function value for continuous functions. In the next segment, we will look at the situations where the function is not continuous.